Everyone, so we are back in week 6. We're going to work on sets 19 and 20 today. We are working with rotational equilibrium and dynamics. So let's start by looking at the assignment we have this week, or I shouldn't say assignment because it's not something that you turn in. Let's look at our discussion tasks for this week. Set 19, we have 61, 62, and 68. All right, so let's start with 61. Here we go. Start with 61. 61 says, for some reason, a metal hoop lies on a horizontal table free to rotate about a fixed vertical axis through its center, while a constant tangential force applied to its edge exerts a torque of magnitude 1.25 times 10 to the negative Newton meters for 2 seconds. A, calculate the magnitude of the hoop's change in angular momentum. Okay, so let's start. As always, if we can, draw a picture so we understand what's going on. So we have a metal hoop lying on a horizontal table. This is kind of odd. Okay. It is rotating about a fixed vertical axis. And there is a force on its edge that's creating a torque. So someone's pushing it, say. Oops. So I shouldn't do that. Force, gonna give it that. Okay, so we are looking for the magnitude of the hoop's change in angular momentum. So we are looking for delta or squiggly L. So let's write down everything that we are given. We are given torque. We are given time. And that's all we're given. All right, so let's write down equations that we know. We know this, where L is angular momentum, I is the moment of inertia, omega is the angular velocity. And we also know tau equals I alpha, where I is the same angle of momentum, or moment of inertia, and alpha is the angular acceleration. So angular acceleration, we know, is omega over t. And we can say that omega equals delta theta over delta t. So we're looking for this, and we're given this and this. So let's play with these equations so that we can get just one unknown in the equation so that we can solve for it. So let's move some stuff around here. If we do this, we can say that gets rid of the alpha and it puts it in terms of omega, which is in this equation. Then we can take this and solve for I and shove it in there. So then we have I equals this Put it in there. And we have rearranging. We get this. That's what we're looking for. These we are given. Let's plug them in, see what we get. We get 1.25 times 10 to the negative 2. I'm going to leave off units. Equals 2.50 times 10 to the negative 2 kilograms meters squared seconds. Just going to leave units off. If anyone is struggling with understanding units or where they're coming from or how we went from something that didn't have kilograms in it to suddenly kilograms in it, let me know and we can discuss offline in my office hours. All right, so that's A. B says, find the change in the hoop's angular speed if its mass and radius are 2.50 kilograms and 0.100 meters. Okay, so now we're given, so we're looking for change delta in this. If this equals this, whoops. And all right, so looking at the equations that we have again up here, we've got this, this. We're looking for this and we're given, and we already know this. So let's write that equation here because we figured that out last problem. So this says angular momentum equals I omega. Well, we have change in angular momentum, but if we have change of angular momentum, then we should have change in angular, not frequency, in angular, what they say, speed or velocity. So we can rewrite this as this. And we're looking for this. And we had that from last time. So let's rearrange. And I is the moment of inertia. That is something that you can look up online. There are some listed in the book. It is specific to the shape of the object and the density and the distribution of density around its center of mass. It is nothing that you will ever be asked to figure out. It is they are constant equations. So looking up online, we have I equals mr squared. So now we can put this in here and this in here, and then it's just what they used to call plug and chug. I don't think anyone says that anymore. Again, I'm going to leave off units. And we were given meters or mass, and we were given radius. Remember this. I want to make sure we got that in there. And then using my calculator, I'm going to get 10.0 radians per second. And that is our answer. That was 61. All right, so let's start on 62. 62 says a disk of mass m is spinning freely at 6.00 radians per second when a second identical disk, initially not spinning, is dropped onto it so that their axes coincide. In a short time, the two disks are co-rotating. This is a fun setup. So like always, we're going to start with drawing a picture. We got one disk You see the direction it's rotating? Spinning freely. So we'll just do this. And then we have another disc. Oops. That's gonna fall here. Drop down like this. And it is not rotating. So let's figure out what we were given here. So we have mass M, which is just the variable that we're going to use. That doesn't really help us. We are given omega of the second disk. So let's say omega 2 is 6.00 radians per second. We are also given omega 1 because it says that it's not spinning. So then it's 0 radians per second. It's really ugly. Not that most of my writing isn't terribly ugly. Oh, I forgot to draw the axes. That's important. All right, so what is the angular speed of the new system? I'm saying angular velocity. This is saying angular speed. The reason that I'm saying angular velocity is because I see omega and I think velocity in my head. They're saying speed because they're not asking for direction. So omega is a vector. So you would have to say this counterclockwise, for instance, but they don't want that. They're just asking for speed. So it is how fast it's moving without how it's spinning, direction it's spinning. So they're asking for, I'm just going to use omega of the new system. So what is omega when the two are together? So we're going to use conservation laws, or you can also look at it as equilibrium, because these conservation says that they have to be the same on both sides. That's what equilibrium means, and it's what conservation means, really. So let's write down equations that we know. We know we're looking for omega. So if we go back to the last problem, we've got this one. And we are going to be using equilibrium or conservation laws. So we are going to say that the initial, I feel like that is easier to see than the eye. The initial angular velocity is going to equal the final angular velocity, and the angular velocity of both is going to be the first one plus the second one, and then the first one plus the second one, but the first one plus the second one become 1. So let's write this out then. So we have L naught 1 plus L naught 2 equals L naught LF1 plus LF2. And we're going to plug this in here, and we're going to say I omega naught 1 plus I omega naught 2 equals I omega F1 plus I omega F2. Okay, there's a couple things that we can do right away. Looks like we don't have enough information to solve for this, just looking at the equation and all the unknowns, but we know that initially the top disk isn't spinning. So we can say this goes to 0. And we also know that these two become 1, and omega is going to be, the same. There's not going to be 2 omegas. And so we can say that this is just 2 I omega, let's just call it F because it becomes 1. So then we end up with I omega naught 2 equals 2I omega final. And we know that the I is not going to change. So the shape of what we've got isn't changing in any way. So these cancel out. And we end up with omega naught 2 equals 2 omega F. And we are looking for omega F. And so we can rearrange this. Omega F equals omega naught 2, which we were given, divided by 2. Plug in numbers. What do we have? 6.6.00. Again, I'm leaving off units. Divided by 2, and we get 3.00 radians per second. And that's our answer. So then scrolling down to B. B says, if a third disk is dropped onto the first two, find the final angular speed of the system. Okay, so we are looking for this real final instead of the pre-final. So what are we given here? We know that what was omega F for the last one is now going to be omega naught for this one. That is 3.00 radians per second. I'm going to assume that that is the one that's dropped has no angular momentum. I think by it saying a third such disk, they're saying the second one had no angular momentum. So then this next one has no angular momentum, and such disk, it's going to have the same mass and the same shape. So I's are going to be the same. So I hate how that comes out. Looks like an H. That looks even worse. Okay, so we can look at the same thing that we looked at last time. We can say L naught equals LF. And so then we have I omega naught equals I omega F. Omega naught we have in the previous one. And we are going to, if we were to write this out completely, we would have, again, I omega naught 1, I omega naught 2. We can just write we can just do 2 I omega naught now, since we have omega naught and we know that there's 2, and now there's going to be 3. So that is going to be equal the angular momentum at the end, and we know that there's 3 disks now, so we can say 3I, because all the I's are going to be the same, omega F, and we are looking for omega F. Wait, are we looking for omega F? Yes, why did I write omega F? We're looking for not L. All right, so I's cancel again. And we have 2 omega naught equals 3 omega F. We can rearrange this to solve for omega F, and we get 2/3 omega naught. Omega naught was omega F in the last part of the problem, and that's 3.00 radians per second. So we get 2/3 3.00 radians per second, leaving units off, and we get 2.00 radians per second as our new angular speed, which, if we stop to think about the problem, that makes sense, because if you have a spinning disk and you drop something on it, it's going to slow it down if it's not spinning. If you put a third one on, that's going to slow it down even more. So that's what we see. We see 6, then 3, then 2. All right, what's the next problem? The next problem is 68. So let's scroll down to that, 68. We're going to start, like always, we are going to draw a picture if we can. Sometimes that's not feasible. A 60-kilogram woman stands at the rim of a horizontal turntable having a momentum of inertia of 500 kilograms meters squared and a radius of 2 meters. The turntable is initially at rest and is free to rotate about a frictionless vertical axis through its center. The woman then starts walking around the rim clockwise as viewed from above of the system at a constant speed of 1.50 meters per second relative to the Earth. Okay, so let's draw a picture. So we have a horizontal turntable, and we got a little lady standing on the edge. Standing there. And she is walking. Does it say clockwise or counterclockwise? It has to if it's asking for direction. Clockwise. So she's moving like this, right? Yes. Okay, so let's write down everything that we're given in the problem, and then we can look at equations that we know to try to solve for what we're looking for. Well, first let's look at what we're looking for. So A says, in what direction and with what angular speed does the turntable rotate? Well, direction and speed are going to give us velocity. So we are looking for omega. Let's look at what we're given. We are given the woman's moment of inertia at 500 kilograms meters squared. We are given the radius of the turntable, 2.00 meters. We are given omega naught, 0. Her velocity is 1.5 meters squared. So her velocity, we need to point out like that. Okay. Let's look at the equations that we know. We have a disk. So looking up the moment of inertia for a disk, we have this. We are going to look at, again, conservation laws or equilibrium, and we can say that angular momentum is going to be conserved, again, looking at this. So we can say that Li equals LF, and we know that L is I omega. So we can write I omega naught equals I omega final. And this is going to be I omega naught turntable plus I omega naught lady equals I omega naught omega F turntable plus I omega, the omega needs to be there. I omega TF, I omega lady F. All right. But we know that the turntable and the lady at the beginning aren't moving it all. So we got 0 right away. So this and this are both 0. So we got 0 equals I omega TF, which is great. We always try to get 0 on one side of the equation. It makes everything so much easier. So we are looking for, what is the direction usually? Oh, okay, the turntable. Okay, so we're looking for this. So we can say negative I omega TF equals I omega LF. And we were given her angular, we were given that. And we were given enough to figure out that. So I is 1/2 r squared negative omega TM equals that was given to us. Okay, so this one I missed up front. Omega equals VR. So then we have negative 1/2 m r squared VR equals I that we're given the lady omega f, which is, this is what we're looking for. So let's do a little bit of work here. And then we're just plugging in. So let's rearrange this to m r v over 2 I L. Let's plug in numbers. What have they given us again? M is 60 kilograms. R is 2.0. We don't need units. V is 1.50. 2 times 500. And I'm gonna use my calculator here, and what I end up with is negative 0.36 radians per second. Now it's asking for a direction. So negative 0.36 radians per second actually is giving you a direction, because originally we started moving counterclockwise. We are going to say now we're moving counterclockwise. So we can say negative, or we can say 0.36 radians per second counterclockwise. All right, B, how much work does the woman do to set herself and the turntable into motion? Okay, so Omega naught is 0. So how much work is she doing to get herself and the turntable moving? So we're looking for work. And we know that work is really just the change of kinetic energy. And kinetic energy for angular for rotational motion is and kinetic energy for translational motion is, we can say like T, and let's say omega equals 1/2 mv squared. So using our conservation laws again, or equilibrium, we know that the change is going to be the final minus the initial. And that we can figure out just with what's given. So I guess we don't even need to use, we don't even need to use equilibrium yet for this one because we're looking at work. Okay, so the change in kinetic energy is just the kinetic energy initially, or sorry, final minus the initial kinetic energy. Let's do not, because it's easier to write. So what is the final kinetic energy? So the final kinetic energy is going to be (1/2 I omega squared. And we were in our problem, we were given those numbers. Final kinetic energy is 1/2. No. Okay, that's right. Sorry, I had to pause there for a minute to look at, I'm looking at the instructions that I posted online and they weren't making sense to me for a second, but now I got it. Okay. So 500 for the woman, 500 is her moment of inertia. And our last problem, we found 0.36. We found omega, so 0.36 squared. This is negative because it's counterclockwise. What is this? So is 1/2 V, oops, we have MV squared, 1/2 I omega squared, and omega squared is V over R squared. So we end up with 1/2 times 240. I'm leaving off the units again. 2 squared. And if I use my calculator, I get delta KE equals 9.9, which is the work required to get her moving equals 99.9 joules. All right, so that was set 19. Let's check my time here. All right, let's go on to 20. All right, set 20, we got 4, 10, 15, 17, and 21. Okay. Using density, pressure, Pascal, and Archimedes principle. Oh, we need to move on to chapter 9. No, it does not want me to go. Chapter 9, fluids and solids. All right. Get to the problem. And we're looking at 4. 4 says, calculate the mass of a solid gold rectangular bar that has dimensions of the dimensions. Okay, so we got a gold bar. Where? Okay, gold bar. We're looking for M. And we're given length, width, height. So we're gonna always put everything in meters because that's what we do. So it's 0.0450 meters. That's length, width, equals 0.110 meters, and height equals 0.260 meters. All right, calculate the mass. And if we go to the book, we're going to see that we've got rho density equals, it's given to us as mass equals rho. No, it's given us as density. Okay, sorry, we're looking for mass. Rho equals mv, mass divided by v, and we're looking for m. So let's find the density, and the density is just length by width by height, which we are given. So we have the volume is length times height. Density is something that we have to look up online. My bad. I'm reading my notes here incorrectly. So let's find volume. Volume equals 0.045. I'm leaving off extra zeros here. 0.11, 0.26, and using our calculator, we get 0.001287 cubed. That's our volume. Rho, you got to look up online. Rho for solid gold is 19,300 kilograms meters. Gold is pretty dense. And then we're just going to rearrange this to solve for M. So we have M equals rho times V. We're just plugging in numbers. 19. Again, I'm going to leave off units times 0.001287. Said I'm leaving off units. I'm leaving off units. And we end up with 24.8 kilograms. All right, so that is our answer for 4. Has a little T next to it because I think we had to go online and find the density of gold. That's what the T means. I forget what T means. Okay, so 10. Look at 10. Oh, a YouTube, huh? Okay. Is there a picture? Oh, there's a picture here. Great. All right, so I'm going to try to draw the picture here really quick. It's in the book. I am terrible at drawing pictures, so I'll just try really quickly to not make it look terrible, which I obviously have. The circle on A. I should have done this before. Just draw it this way. Right? Oh, I don't know. It's not any better. Okay. Mercury is poured into a U-tube as shown in the figure. The left arm of the tube has cross-sectional area. 10.0. Oh. No, we'll leave it in centimeters because it's squared, so we got to change it too, and we'll use that in our calculation. The right arm is a 2 equals 500 centimeters squared. 100 grams of water are then poured into the right arm as shown. So we have like this. Oh, let me. So we would have like, here's where the mercury is. It's going to be level kind of in the U, but then when you pour water in, it's going to push the mercury up. So we're going to have something that looks kind of like this. Drawing the picture. All right, so what are we asked to find? We should have found that before we write down what we know, but that's okay. A, determine the length of the water column in the right arm of the U-tube. So we are looking for L. Let's do that. Little R there. And I already wrote down what we are given. So we know that rho equals MV, like we used last time. We know the mass of water. So that's not given, but we know that. You can go online and find that. It is 0.1 kilogram. Let's say that's mass of water. So let's find the volume. because we know that whatever that pushed up, that volume is going to be the cross-sectional area times the length that it pushed up. So we can look up row of water. Also, the density of water is 1,000 kilograms per meter cubed. Okay, so let's solve for volume. We're going to take that and we're going to move it around. We're going to say V equals rho over M. We are just going to plug in 1. This is pretty easy calculation to do here. Did I enter? And we get 0.0001 meters cubed. Oh no, I wrote this wrong. Sorry. Just looking at the one above. M over V. So these are swapped because this is M over. Okay. That doesn't work out. All right. So then we get that. Now we have the volume equals this. And we want to solve for L. So LR equals V over A2. We've got V as 0.0001. So now we're going to write out units because we need to take this from centimeters squared into meters squared. So the very common mistake when, not even just do it like everybody, when you are changing units, so we want to go from centimeters to meters, or if we want to go from meters to centimeters, I don't know why you would ever do that, but if you are doing that for some reason, you have cubed or squared, and so it's not just 1, it's 2 that you want to change. So it's easy to see that when we use units here. So when I do enter A2, which is 5.00 centimeters squared, these don't match. So we need to change centimeters to meters, or again, meters to centimeters, but I'm not sure why you would want to do that because SI says meters. So let's do 100 centimeters in 1 meter. So now we've gotten rid of 1 centimeter. Now we need to get rid of the other one, 100 centimeters per meter. And then we got rid of that. And if we take that out, we are going to now have 0.0001 over 0.05 meters squared. We've got meters cubed, and we want just meters because we want a length. So we end up with 0.200 meters. So that is our length of the right side of the tube. That was A. B. Given the density of mercury, so rho M. Oh, let's write down what we need first. H of the mercury. So our H is going to be this here. given that rho of mercury equals 13.6 grams per centimeters cubed. Now let's go ahead and change that right away. We're going to use SI units. So we're going to go right away to meters and kilograms. So kilograms, 1 kilogram is 1,000 grams. And again, there's 3 centimeters. So we want to get rid of all 3 of them and get to meters. So we have 100 centimeters over 1 meter, 100 centimeters over 1 meter, 100 centimeters over 1 meter. And we end up with 2, 1, 2, 1, 1. We have rho of mercury equals 1360 kilograms per meter. Okay, so for this, we're going to use Bernoulli's principle, which we were introduced to in this chapter. Bernoulli's is fun with fluids. And Bernoulli's is going to say P1 plus 1/2 rho V1 squared plus rho G Y1. We're going to say Y because we're up and down, not side to side, equals P2 plus 1/2 rho V2 squared plus rho GY2. Okay, let's see if we can get rid of anything right away and make this simpler, because this looks like we can't solve it right now. So 1/2 rho V1 squared, well, V1 is going to be, this is going to be 0, because it's level for 1. And well, I guess for 2, it's also going to be 0, because we're looking for each on each side. So this is also going to be 0. I guess I said that incorrectly when I started here. Okay, so P1 is really going to be P water plus rho water G Y1, and P2 is going to be P mercury. So P mercury plus rho G Y2. All right, so we should have put that there. Okay. So rho water and rho mercury are things that we can look up. Those are just constants, and we can rearrange this to find what we're looking for. So we are looking for this, because that is the height of the mercury on the other side. So we can do H equals P minus P plus rho water GY1 all over rho HG. So PW equals pH. So these we can just say go to 0. And we end up with, oh, and these also cancel out. Sorry, I missed that. And so we end up with rho of water, Y1 equals rho of mercury. And we found Y1 in A. So that is the height or the length of the water in the column. So this is just plugging in what we have, what we know. I'm going to leave off units again. 0.2. Well, we do want to do this just so we can be consistent with significant digits. All right, and this is all right. So if I use my calculator here, I get 0.0049 meters, or write it as 4.9 times 10 to the negative 3 meters. So that is the answer for B using Bernoulli's. $15. $15 says a sphygmomanometer, good heavens, is a device used to measure blood pressure, typically consisting of an inflatable cuff and a manometer used to measure air pressure in the cuff. Oh, this is just getting air pressure, getting your blood pressure measured. In a mercury, that word, blood pressure is related to the difference in heights between the two columns. This makes sense. The mercury thing shown in the figure contains air at the cuff, pressure P. The difference in mercury heights between the left tube and the right tube is 0.11 meter, a normal systolic reading. What is the gauge systolic blood pressure in pascals? The density of mercury is this, and the ambient pressure is this. Okay, so let's draw this really quick. What they have here looks like this. And then okay. So P, and they have a label P and P not. And we are looking for what is P gauge? Okay. Let's write down what we're given. We are given the height of the right tube, 0.115 meters. We are given rho of mercury, which we were given last time also. Just looking at the problem, the last problem. It equals a different, anyway. 13.6 kilograms per meter cubed. Oh no, that's right. Okay, times 10 to the 3. Okay, I'm it's really thrown there. We are also given P naught was 1.01 times 10.5 PA. We're given it in pascals. That all we're given? Looks like that's all we're given. All right, so we're looking for PG, and we know that PG equals rho GH, and we are given all of the unknowns. P, we're given rho G and H, so we just have to plug those in, and we get rho 13 that off times G meters per second, leaving off units, times height we're given 0.115, and if we use our calculator we end up with 1.53 times 10 to the 4 pascals, and that is our answer. All right, moving on to 17. Moving on. 17 says, buoyant forces and Archimedes principles. A table tennis ball has a diameter of 3.8 centimeters and an average density of 0.0840 grams per centimeter. What force is required to hold it completely submerged underwater? Okay, so we are looking for force underwater. So let's say force U. And we are given diameter. So radius equals 1/2 of diameter. So we've got 3.80 divided by 2. This is centimeters. So we're going to want to change that right away. So 100 centimeters over 1 meter. That oops, 380 meters 2. And we're also given the average density equals 0.0. Change that one right away too. 1,000 grams, 1 kilogram, and 100. Oops. 100. All right, so we're looking at buoyant forces and we're looking at Archimedes principles. So we know B equals rho BG. So the force is going to equal what you've got to push down. So the force pointing up is going to be the force that you have to push down. So we've got F of water is going to equal B minus rho VG. Where this is of water, this is of the tennis ball. So B is rho VG. So we've got water G minus the tennis ball. So rho tennis ball VG. And volume of the sphere that will be the tennis ball. So V is 4/3 pi r cubed. So let's just plug in numbers now. Equals rho of water is 1,000 kilograms per meter, which we got in a previous problem, times 4/3 pi. Up here we've got 0.019, that is cubed, times 9.8 meters per second, because that's G, minus the rho of the tennis ball, which we were given. Times the volume again. Times 9.8. So if I were to get out my calculator and do the calculation, I end up with force equals 0.258 newtons or kilograms meter per square, which is what it comes out to if you take the units all the way out. All right, so 21 is our last problem here. 21 says, a hot air balloon consists of a basket hanging beneath a large envelope filled with hot air. A typical hot air balloon has a total mass of 545 kilograms, including passengers in its basket, and holds 2.55 times 10 to the third meters of hot air in its envelope. If the ambient air density is 1.25 kilograms per meter cubed, determine the density of hot air inside the envelope when the balloon is neutrally buoyant. Neglect the volume of air displaced by the basket and the passengers. Okay, so we are looking for the density of the hot air inside of the balloon. So let's say rho I of inside. And then let's write down what they've given us. They've given us quite a bit here. So typical hot air has a total mass. Let's put T just for everything. 545 kilograms. And holds, so volume is 2.55 times 10 to the 3 meter cubed. That's big. And the ambient air density, so the air density outside is 1.25 kilograms per meters cubed. Okay, so we want the hot air inside the envelope. So when it is buoyant, when they are matching in essence. So we know that equals rho VG. And that is not enough to solve this. But we know Second's law, Newton's second law, is F equals ma. So we're given the mass here, and we know acceleration is 9.8 meters per second towards the center of the earth. And the buoyancy is a force, and so the force is going to equal ma. So we can say that force equals ma equals rho vg. So ma equals rho vg. A is the acceleration due to gravity, so a and g are the same thing. And rho is the density of the outside minus the inside. So it's the overall density because they're matching. So we can write m equals rho of the outside minus rho of the inside times volume. And the volume we're given. And we want to rearrange this for rho I. So rho, rearranging, we have rho I equals rho of the outside minus m volume. And these are all givens. So we just need to plug in numbers. 1.25 minus 545 divided by volume. Wrote that wrong. And we get rho I equals 1.04 kilograms per meter cubed. All right, so that is the answer to 21, and I will see you for the next set of problems.